All right, good afternoon, everyone. Welcome to our ITS seminar. Today, we're very delighted to have Professor Fred Mannering as our speaker for today. Professor Mannering is the current Associate Dean for Research in the College of Engineering and a Professor of Civil and Environmental Engineering at the University of South Florida. He also holds a courtesy appointment in economics. Before joining University of South Florida, he was a professor at Penn State, a professor and department chair at the University of Washington, Seattle, and school head and chair professor at Purdue University, all in civil and environmental engineering. Dr. Mannering's research focuses on applications of econometric and statistical method to the analysis of highway safety, transportation economics, vehicle demand, travel behavior, and a variety of other engineering-related problems. He has published extensively in these areas, and his work is highly cited. He also co-authored two popular textbooks. One is Principles of Highway Engineering and Traffic Analysis, which I use in my undergraduate course here for more than 20 years. Another book is called Statistical and Econometric Method for Transportation Data Analysis. Professor Mannering is currently the editor-in-chief and also the founding editor of the Elsevier Science Journal Analytic Method in Accident Research, and a previous editor-in-chief and current distinguished editorial board member of the Elsevier Science Journal Transportation Research Part B, Methodological, one of the premier transportation journals in the world. So this is his official bio, but I would like to let you know that when he's not doing all the above, he plays rock music and also races motorcycles. I'll let him to tell you how he managed to do all this with the time he has. Fred, now the Zoom room is yours.
Okay, so maybe I'll talk about the rock and roll and the motorcycle at the end of the lecture, right? Yeah. Although I do have my guitars, a couple guitars out in the background. And in the corner here, I guess it's this corner, that's actually a cutout of Johnny Depp from Pirates of the Caribbean. It doesn't quite show up in the Zoom screen, but it does in the Microsoft Teams as a wider angle, it usually shows up. So today, before we got started, we were talking about machine learning. So today's talk, I'm going to talk about different methodological approaches from traditional statistics to more advanced, what we call heterogeneity models that use mixing distributions, to causality models, and then to sort of full out machine learning. So we're going to look at the differences in these, and the application that I'm going to provide today is for highway safety, but a lot of these same issues that I'm going to talk about today come up with almost any transportation related data, and even beyond transportation related data, these elements will come up. So first, I'm going to look at and mention that today's talk is really based on two papers. One is a paper that I recently wrote with Chandra Bhat at UT Austin, Venki Shankar, and Mohammed Abdel-Aty, who's actually a University of California, Davis graduate. I should mention, is a little departure, I was on sabbatical leave at the University of California, Davis in 1992-93 academic year. Probably a lot of the people here today weren't even born then. But Mohammed Abdel-Aty was a doctoral student at that time, and we shared an office. And so that's how we got to know each other. But so that's going to be the primary paper that will contain the material that I'm talking about today. But I also have a 2018 paper that talks about temporal instability in the analysis of highway accident data, but there's temporal instability in a lot of transportation related data, and I'll talk about that a bit in this talk as well. And I want to special thanks to Clifford Winston at the Brookings Institution, who was actually my doctoral advisor at MIT, because we talked for years about some of the concepts that I'm going to be talking about today, because he's a full economist, and I'm sort of an engineer / economist. So we have a lot of debate about endogeneity, self-selectivity, all these things that we'll chat briefly about in today's talk. So let's look at highway accidents. And if we think, when you look at the infrastructure bill that might be coming out of Washington, D.C. At some point, safety is one of the key issues that will be addressed in that. But there's a lot of elements that are coming up in highway safety, like autonomous vehicles and how people's behavior will change around autonomous vehicles, because until we go to fully autonomous vehicles, we're going to have an interesting mix of people-driven cars, human-driven cars, and autonomous vehicles. And it's going to be an exciting 10 to 20 years of research until we get fully autonomous vehicles. Then the mode is going to change. But the way people's behavior is going to change around autonomous vehicles is going to be a fascinating research topic for many years. So if we look at highway accidents, use about the general consensus, 1.2 million people per year, probably 50 million more injured worldwide. And safety researchers have sought for decades to reduce this carnage by doing some sort of statistical analysis, mostly statistical analysis, although neural networks and other methods, data-driven methods, were also used, and I'll talk about that in a moment. When we look at the analysis of highway accident data, studies have really focused on two elements: the likelihood of an accident, and then the resulting injury severity. And when you look at the likelihood of an accident, usually have accident counts per some period of time, and then the resulting injury severity, usually police reported data are used, and they use a 5-point injury severity scale: no injury, possible injury, evident injury, disabling injury, and fatality. And the way that the accident data are recorded, you have 30 days to die. So if you're in a crash and you don't die within 30 days, you'll be listed as a disabling injury. If you die in the 31st day, you won't be listed as a fatality. But when we look at this, and again, mostly from police reported data, you can safely say that many insights have been gained by the analysis of these data, but there's some very critical elements. One is the using police reported data is going to have some issues, and I'll talk about that in a second. We have vehicle driver data, because we now have some naturalistic driving studies where you collect very large amounts of data. Even you could look at like eye movements of the driver, very detailed data, so, far beyond what's police reported data. Then we have site observational data, where we can use videos and sensors to see not necessarily if there is a crash, but how close vehicles came to crashing. And so there's a whole body of research that looks at time to collision and sort of methods like that are based on observational data. When we look at police reported data, that's the most widely used and available. And if you look at a police reported data, there's a lot of information in there. But there are some problems with police reported data. So and I'm sure some of you have been in accidents. The police go to the scene, they fill out the age of the driver, they get a lot of information on road conditions. So there's probably hundreds of variables. And if you link it to state databases, you can link it to the coefficient of friction of the highway and all sorts of things. So you can very large amounts of data. But there's an underreporting of minor crashes, because a lot of minor crashes aren't reported to the police. So that's always a concern. There's potential inaccuracies in the attributes and injury severity levels. Like I mentioned at the beginning, if you die in your 31st day in the hospital, you're not recorded as a fatality, you'd be recorded as a disabling injury. So there's possible some inaccuracy in that and other attributes. And most importantly, and this is going to be one of the concepts I'm going to talk about throughout today's presentation, is it's only gathered for people that are observed in the crash. And so this is something economists spend a lot of time on, is sort of this self-selectivity and identification issue. And I'll explain this a little more in the slides forthcoming. But we do not have the people that are actually observed involved in crashes are a self-selected group of probably more crash-prone drivers. We do not, ideally what an economist would do, an experimental economist, is they would develop an experiment and have everybody drive into a brick wall or something, and then they would have a sample that fully captured, a complete sample of the population. But since we're dealing with a self-selected sample of risky drivers, that has implications for the types of models we use and the conclusions that we draw. So again, I'll get into that in a little more detail in a second. For naturalistic driving data, here you gather massive amounts of data because you have a fully instrumented car. So you're going to get acceleration, deceleration, yaw rates, all sorts of things. But this has problems with the subject selection. The people that actually use these cars have to be generalized to the entire population. The behavior of drivers includes route and time of day choices that are self-selected. So you still have, even the safer drivers are going to probably go on what they feel is a safer route. So the route choice and all of these things still have sort of a self-selectivity in them because we don't observe the safest drivers maybe on the most risky routes. So you might think is like, oh, that one intersection is dangerous and I just try to avoid that. So that's going to create a potential self-selectivity problem as well. That's going to affect the identification of parameters when we estimate these models. And the other things with naturalistic drivers is you tend to have few observation of catastrophic events because you have a limited number of vehicles that are fully instrumented and you don't actually observe them in a crash. I should tell you that it reminds me, and I'll diverge for a minute because we talked about motorcycle racing, and one of my crashes was on the Las Vegas Motor Speedway. I was invited by Honda. They were testing back then, it was the CBR 600RR. I think these were in the early 2000s. But anyway, I crashed and they figured, oh yeah. So they had some racers go to the Las Vegas Motor Speedway to test this new motorcycle. And they were collecting all sorts of data on the fuel injection and the acceleration, deceleration. But after I crashed, I figured, well, that's it, I'm going to be out. But it said, no, go back out. Because when you crash, you get an incredible amount of information. So they were hoping I'd go out and crash again or something. But anyway, that's I hadn't thought about that story until now. But so there are, I've thought about the story before, but I haven't thought about the analysis here. There's great information when you actually have a catastrophic event because you get a lot more data than if you don't have a catastrophic event. So there's also site observational data. So here, as I mentioned previously, we have massive amounts of data gathered from video and potential sensors and other things we may have in the roadway. So these data have problems because we don't gather the socioeconomic characteristics of the drivers. We usually don't observe all the details of the drivers. The behavior of observed drivers still has this route and time of day choices that are self-selective. Again, you have the case where it's a dangerous intersection. You're not observing all of the people because some people may avoid dangerous intersections. And again, we also have here few observations of catastrophic events because your probability of observing a crash at a specific intersection, you may get one a day or one a week. So there's not going to be a lot of catastrophic events. So let's look at what are the analytic alternatives. Now, these are the analytic alternatives that have been applied in safety studies, but you could think of this in almost any data that you might analyze that's in transportation or really in any field. So we have what I would call traditional statistical models. So these are things, models that you probably had in a lot of your statistics courses, ordinary least squares, multinomial logit, all of these standard fixed parameter models that you probably know, hazard-based duration models. If you look at my textbook, which was mentioned, statistical and econometric methods, almost all of these models are in there for the first 15 chapters. But starting in chapter 16, and this is sort of 16, 17, and 18, we start looking at the heterogeneity models. Now, heterogeneity models, probably the one that you may have been exposed to is like a mixed logit model. So these models have mixing distributions in the parameters to try to capture what is commonly referred to as unobserved heterogeneity. So these heterogeneity models at a level of complexity that attempts to capture all sorts of unobserved elements of the data. So these heterogeneity models have become the most popular model used in sort of advanced safety work. There's random parameter models, latent class models. All of these models I would classify as heterogeneity models. Next, we have the data-driven methods. So this is the machine learning, neural networks, all of the stuff that just analyzes a correlation and patterns in the data without necessarily much thought to underlying causality. And I'll talk about what I mean there in just a second. But lastly, we have what I would call the causal inference model. So this is, if you look at the economics profession, this is where modern economics is really focused on what I would refer to as causal inference models. Economists focus on uncovering causality. And in so doing, they're going to have to make compromises and stuff, but they really want to understand what is driving the underlying process. Where some of these other models, to varying degrees, ignore causality. And I'll explain the details of that in a second. So let's first look at traditional statistical models. So if you've had a course in high school or undergraduate, this is probably what you've ordinary least squares, regression, 3-stage least squares, 2 stages, all that stuff I would classify as what is a traditional statistical model. So it uses conventional statistical methods. And this is if you use the highway safety manual or you're familiar with the safety field, these are the models that are used for safety practitioners. There's a claim of predictive capabilities and causal explanation, but there's a general lack of fundamental support for these claims, and I'll talk about that in a second. And a lot of times you can easily show that the parameter estimates are biased because to develop models that can be used in the field, a lot of times you don't have access to very large amounts of data that you need. So there's an omitted variable bias. So there's a lot of times if you use a traditional statistical model, you end up with omitted variable bias and other issues that I'll talk about soon. Now, if we look specifically at the case of highway safety analysis, we have Poisson and negative binomial regressions. Because remember what I talked about, we're looking at the likelihood of a crash and then the injury severity of a crash once a crash has occurred. So when we look at the likelihood of crashes, we usually want to look at the number of crashes per month, number of crashes per year on a highway segment, or perhaps at an intersection. And since these are non-negative integers, we usually use count regressions. You don't want to use a normal ordinary least squares regression because you don't account for the fact that that's a non-negative integer and you end up with a continuous variable. So Poisson and negative binomial regressions are most often used for that. But there's also been applications of a Tobit model where you have censoring at 0 because a lot of intersections or highway segments that you analyze over some length of time may not have a crash during that time. So there's going to be a 0. So Tobit models have been applied. And just sort of a background, the Tobit model was developed by Tobin, who was a economist. I think he won the Nobel Prize in economics. He developed a model, Tobit model in 1958, won the Nobel Prize maybe in the 1970s, but not for the Tobit model. We'll talk about other Nobel laureates later in this talk that actually won the Nobel Prize for the methods that I'm going to talk about today. Then we have ordered probit model and multinomial logit models that are often used to determine the injury severity of crashes. So as again, if you recall, I mentioned there's 5 injury severity levels: no injury, possible injury, evident injury, disabling injury, fatality. These are discrete alternatives. So we apply an ordered ordered probit model, ordered probability model, could be ordered logit or whatever, and a multinomial logit to determine the probability of those outcomes. Now, the heterogeneity models use these traditional models as a starting point and then add mixing distributions to account for unobserved effects. So the idea with these models is that, well, you know, I know that there's, everybody has a beta, some beta in the population, but some people may have different betas than other people. So using these mixing distributions, and this gets to the mixed logit, all sorts of random parameter models, you can mitigate potential parameter estimation bias and provide additional insights. But at the downside, the model complexity can be very extensive, because you can look at using mixing distributions with heterogeneity in the means, heterogeneity in the variance of the distributions, and you can even have correlated random parameters. It can become a very complex thing. But what I'm going to show you, though, is that these heterogeneity models are sort of a link between traditional statistical models and almost like a machine learning. You know, they fall somewhere in the middle. And I have a nice little diagram at the end that will show where these various methods end up. So the heterogeneity models expand traditional statistical models with random parameter models, heterogeneity in the means and variance, correlated random parameter models, latent class models, also called finite mixture models, latent class models with random parameters, Markov switching models. And, you know, if you want to get into this, you know, into these mixing models, just send me an email and I'll send you some, you know, great papers on these things. But, you know, these are going to have issues with them, as all of the methods I'm going to talk about today have. So let's look at data-driven methods, because this is the big fad now, right? Because this can handle extremely large amounts of data, provide a high level of prediction accuracy. I mean, if you look at machine learning, even neural networks and stuff, the prediction accuracy is amazing. The downside is that you don't necessarily provide insights into underlying causality. So if there's some fundamental shift in behavior, these models do not predict well, do not forecast well. In real time, they're very good because you're unlikely to have these, what we might view as a temporal shift in the betas. But if you're using machine learning to predict 2 or 3 years out, it can be problematic because you're not getting insights into causality. So data-driven methods, data mining, artificial intelligence, machine learning, neural network, these are methods that analyze the correlations and the complexities of data, but without really putting an emphasis on underlying causality. And that gets us to what the economists are using a lot. And this has become a big thing in the economics field with experimental economics and so on, is they explicitly recognize what an economic model would, an economist would do, is explicitly recognize that accidents are only observed for a portion of the driving population, and that this can lead to erroneous interpretation. Now, when you have this sort of self-selected problem, is that you're not observing everybody getting into an accident, there are corrections for that. There's a mathematical correction, and then there are methods where you can use fixed effects and other ways to mitigate this potential problem. The downside with these causal inference models, and as I'll explain in a few minutes, is you cannot provide the level of detail that's often needed by practitioners. For a causal inference model to be implemented, usually you have to simplify the data to such an extent to be able to uncover the underlying causality. So causal inference models are typically based on ordinary least squares regression, which has great properties. It has great small sample properties that make it ideally suited to this. And usually to account for the endogeneity and self-selectivity that's encountered, they can use instruments, fixed effects. There's a lot of tricks that can be applied to try to avoid this issue that you're not observing everybody getting into an automobile crash. So let's look more at this causality and the identification problems. So here's when you want to determine causality, we give you safety examples. Again, I mentioned crash data are a selective sample because we only observe individuals who are in crashes. Individuals observed in crashes may not be a random sample of the population. You know, for sure they're not a random sample of the population, but on one level, everybody has a probability of getting into a crash. But since we don't have a fully random sample, this can create problem in identifying causality. And this identification problem has dominated the economics field. I think they've gone overboard in economics, but if you look at engineers and how we've analyzed data, we probably have not given enough thought to this. So somewhere in the middle of what we're doing with our heterogeneity models and what the economists are doing with their causality models is sort of a happy medium. So this has dominated many fields and has also given rise to like experimental economics. So let me give the great example of this, and because I'm a motorcycle rider, this really makes this sort of self-selectivity problem really clear. So let's say we estimate an injury severity model. So we're developing a model that predicts a probability of a motorcyclist that, you know, condition on them being in the crash. What is the likely outcome of that crash? You know, and we could use the 5: no injury, possible injury, evident injury, disabling injury, and fatality. Suppose we have an indicator variable, whether it was raining at the time of the crash. So, and we find that that indicator variable has a positive effect on being severely injured. So we find that the rain indicator variable increases the severity of the crash. So the problem is that becomes difficult to interpret because we don't know if the rainy conditions, actual rain increases the severity of the crash, or what we're observing is that safer riders just don't ride in the rain. And so the people that we observe in the rain are just dangerous riders. So when we get that result in our model estimation, we can't interpret what the effect of rain is because we're not sure if it's actually the reduced friction that's causing the increase in severity, or the fact that now we're just observing the riskiest drivers, and the riskiest drivers are more likely to be severely injured when they crash. So this is the problem that economists try to uncover with the causal inferences. They try to untangle the effects of the actual physical element of rain and the self-selectivity of riders not riding in the rain. And I can tell you as a motorcycle rider, I do not ride in the rain. Yeah, it's like I know how the bike performs in dry conditions. Same thing on racetracks. I don't race in the rain. So if it's raining, I'm out of the race. So I just don't want to go there. So with the motorcycle example, this creates identification problem because, as I just mentioned, does rainy weather increase the injury severity of all riders, or does rainy weather have no effect on the injury severity? And our findings simply reflects the fact that injury-prone riders are more likely to ride in the rain. So in this case, it may be a combination of the two effects, but we're not going to be able to uncover that unless we explicitly address this self-selectivity issue. So identification is an issue in other transportation data analysis. So this is not just injury severity and highway safety. So if you look at equity studies, underprivileged are going to be underrepresented in many samples. So if you're looking at, how's Uber going to be applied to disadvantaged people, you're going to have a self-selectivity because any data you observe, you're going to probably underprivileged people are going to be less represented in the Uber sample, and this is going to create this self-selectivity problem. Individuals observed on specific routes are a self-selected group. And chapter 15 of my Statistical and Econometric Methods textbook actually addresses this specific sample. So there, if you look at the chapter 15, I have people from a single origin to a single destination choosing 3 different routes, a freeway, an arterial, and a rural road. But the thing is, you only observe people taking one of these routes. Probably the fastest drivers go on the freeway, And if you close the freeway, you don't know how they're going to behave if the fastest drivers were going other routes. Ideally, you would set up an experiment where you had everybody go on each of the routes and then observe their travel times and behavior. But since we don't have that, we have an inherent self-selectivity problem. Now, this, the example 15 in the book is a simple ordinary least squares model that tries to predict the average speed of people on these different routes. And there is a correction for that. James Heckman won the Nobel Prize, shared the Nobel Prize in 2000 with Dan McFadden, on his Heckman style selectivity bias correction. So that's what the chapter 15 looks at that. But I'm going to talk about the Heckman correction in a few minutes. So I just want to mention that now. So individuals observed driving only one type of vehicle, actually going way back to 1983 when I did my dissertation on vehicle ownership and vehicle use. Back in 1983, I was like 5 years old. No, that's a joke. Let me see. Wait, I got my... Actually, yeah, again, probably, way more than half of you were born in 1983. But that was an issue that I had to address in my dissertation because, again, you don't observe, you can look at it. We know that people that own new cars drive more than people that own used cars, but we don't observe people that always have used cars. We never observe them driving new cars. So we have a problem is that for old and new cars, you don't observe everybody. So it's the same sort of self-selectivity problem that we're talking about with route, and then also with people getting into accidents. So there's similar examples that pervade transportation modeling, modeling based in observed data. So dealing with self-selectivity, identification, causality, we can look at the traditional models that I talked about, which is like the ordinary least squares. They do not address the self-selectivity. The data-driven methods, machine learning and so on, does not address the self-selectivity. Heterogeneity models mitigate the effects with mixing distributions, but they do not solve the problems. And you have to make distributional assumptions. There's a lot, so you're getting some mitigation of the effect, but you're still going to have it. Causal inference models explicitly solve the problem, but to do so, often they must greatly simplify the data using fixed effects, instrumental variables, and other things. So if we look at this sort of self-selectivity, identification, causality, in heterogeneity models, the problem can be theoretically solved with this Heckman style correction. So this is the chapter 15 from my textbook. You can, if you have ordinary least squares, you can develop this Heckman selectivity correction. Again, he won the Nobel Prize for this. But if you extend that to the nonlinear models, like logit models, probit models, that we use in highway safety, it's a mathematical nightmare to do a selectivity correction in a nonlinear model, especially when you have a nonlinear model with mixing distributions. So it's just not possible to do a traditional Heckman style selectivity correction. So when you're deciding what methodological approach to use, and almost any of you that are doing like dissertation, thesis, or whatever, if you're using some methodological approach, you probably say, oh yeah, I'm going to use machine learning because everybody's doing that now. You should think about the slides in this presentation and what that means, because it'd be a nice sort of summary to put the method that you use in the context of the available methods. So, but when you're thinking of which methodological approach, you can think of the following considerations. One is the predictive capability, the ability to provide detailed usable findings. The second would be causality, the ability to understand the causal elements of the occurrence and injury severity to guide policy decisions. So this is something that economists would focus on. And then just the data characteristics. I mean, if you have hundreds of millions of observations using traditional statistical methods or heterogeneity models, just not going to be possible. So the data characteristics and size also plays an element. Now I have this diagram that sort of shows how how each of the approaches that I discussed sort of fit into this these predictive capability, big data suitability, and causality inference capability. So if we look at the causal inference models that are outlined in the yellow here, I guess I can move my pointer over here. If we look at these in the yellow, this is what economists, when you think of economists, the data that they analyze, they are very interested in causality. And since they focus so much on causality, they compromise predictive capabilities because they can't have the very large amount of data that is often required for good predictions. And they also are not suitable to big data. If we look at the second sort of model, which would be traditional safety models, which are in this blue area, you get a little bit of causality, a little bit of predictive capability. With the heterogeneity models are pretty good with predictive capability. Pretty good with big data, and they're very, better than causality. Not as good as a causality model, but better than traditional statistical models. And if we look at data-driven methods, so we have the heterogeneity models are green are going to be tilted toward the right of the triangle. And the data-driven methods have excellent predictive capabilities, unless you go like 5, 6 months, years, 7 years out, then you start getting shifting temporal effects. But they're very obviously with the large data, they have excellent big data capabilities. But on the downside, they're not going to uncover causal effects. So you can sort of look at these 4 basic methodological approaches and see how they fit into the predictive capability causality. So really when you're selecting a method, you're making some compromise no matter what method you choose. Now, the method that I've been using in my research is sort of this heterogeneity model. So you can see it doesn't do anything the best, but it does everything a little bit, is a little bit well, it does everything a little bit well, but not anything great. So when we look at the current state of traditional safety models, so let's look at these methods and see where everything stands. Simple statistical methods continue to dominate safety practice because they're real easy to use. And these models form the basis of the Highway Safety Manual and efforts to improve it. For heterogeneity models have rapidly evolved to dominate the safety literature. But in practice, people have not understood their application very well. So one of the problems with heterogeneity models, so if you have a random parameters model, a lot of people have been erroneously using the mean of the random parameter that was estimated in a heterogeneity model. But really, there's a couple papers that have come out recently that show you have to use the variance as well, or it provides obviously biased results. So the practical application of heterogeneity models, even though they've taken off in the academic literature, it's still going to probably be like 5 years before they hit the practical literature. For data-driven methods, these are the current fad, gaining wider acceptance, have obvious applications in real-time data processing, where issues of causality are of little concern. There's going to be a big place for data-driven models, obviously, in the future. For causality models, they really have not gained a lot of traction in the safety field for 2 reasons. They do not have the potential, for example, to handle detailed predictions. So for example, a lot of times you have a specific highway. It's like, okay, I want to increase the shoulder width from 4 feet to 6 feet. How's that going to affect the frequency of crashes? To be able to make that kind of prediction, you need pretty detailed data. And usually, if you want to undertake a causality model that addresses that self-selectivity question, you're not going to be able to answer a question like that. But if you don't account for the causality, you'll be able to answer that question. There's probably going to be some error in your estimate, though. So safety researchers have not really thought much about the selectivity problem and the impact that it has on estimates. So the extent of this problem is not known yet, although there are a lot of recent papers that are going to start looking at this self-selectivity problem. There are a couple that have already been published and a couple that are under review in the journal I edit now. So the future, when you think of these different methods, you're probably going to end up with some mix between heterogeneity models and data-driven approaches. That seems to be the most fruitful direction. So heterogeneity models can still potentially unravel some causality effects, but you're probably going to see some hybrid approach between machine learning and the heterogeneity models, which sort of link back to the fundamental statistical approaches. But there also needs to be very serious thought has to be given to this self-selection identification problem, which again has largely been ignored in the safety field. So again, if you look at this sort of diagram, you can see here that, again, all of the methods are going to have the trade-off, but we've really been shortchanging the causality inference capabilities of the model. And if we look at the individual ones, you can see that the data-driven methods, if you look at what data-driven methods and heterogeneity could potentially bring, you can see we get to almost all the ends of the triangle. I mean, we're still losing some on causal inference and a tad, but it seemed that some combination of data-driven plus heterogeneity methods could get a pretty big area in this triangle. So, sort of a summary and conclusions. I think an ideal model would be one that uncovers causality, has excellent predictive capabilities, and scalable to very large data. But with currently available methods, safety analysts and analysts in other fields are going to be forced to make a trade-off that can entail serious compromises. There's a clear need in safety, probably other transportation fields as well, to ground intrinsically predictive models, which are like machine learning with causal frameworks. So intrinsically predictive models, especially for big data, can also improve causal structures through insights from association involving variables not typically available in traditional safety data. The promising direction for future research, I believe, is a hybrid approach for data-driven and statistical methods with strong consideration for causal elements. Such a hybrid approach is likely to be perfected over time as an integrative technique and access to more big data becomes available. So that's sort of the outline. I'm not sure how we're doing for time. I guess we're okay.
We're doing great. Yeah.
Good, good.
Well, thank you, Fred, for just really a great overview of the landscape of safety modeling using statistical tools. And as you mentioned, this also, the similar problems also exist in other data analysis for transportation, like we have travel surveys for, for example, carpooling or other applications. Yeah. So I would like, now open up the Q&A, and I want to remind our students that, you use your raise hand sort of function to ask questions, and for our outside audience, you can use the Q&A to post your questions. Since some of our audience are the students, the rich for the class, and so we'll have them to ask questions first. But before we, start the Q&A, remember in the start, I think we would like to hear a little bit more about Fred's other interests that, and sort of, he's not your sort of usual professor, and so it will be interesting, good to know how he, his trajectory as an academic, and I know many of our students who have an interest, into academic career will be interested to know, and also know that a professor is not just writing papers and writing books.
Okay, let me share my website here. So Yeah, I had, because again, everybody has a life outside of academics. So a couple, interesting things that I've done over the years is motorcycle racing. So most of this was actually in the early 1990s, although I still did track days and stuff until the 2000s. But this is a picture of me testing, I think, yeah, this isn't the one I crashed on, but this was during that, this I think, I'm not sure how many are motorcycle, especially older motorcycles. I think this was the CBR 600RR that I actually crashed on maybe a day after this was taken. But anyway, I always had the really cool helmets. So, I had the dragon with the fire coming out and stuff. So, but motorcycle racing is very dangerous, but it's very attractive because, motorcycles go 0 to 60. The bike that I have now, which is this CBR 954R, is like 0 to 60 in 2.5 seconds. But I was reading today that Tesla is coming out with a roadster that goes 0 to 60 in 1.1 seconds. So you may have seen that story. I think it just came out today, actually. So, and these are some of the cars and motorcycles I currently have. But the other sort of interesting element, and everybody can think about this, in the early 90s, I was in a heavy metal band in Seattle, and this was when Nirvana, Soundgarden, everybody that was anybody was from Seattle. So, and we did a CD. We had interest from, there was Metal Blade Records in Los Angeles was interested in. So at the time I just returned from UC Davis, my UC Davis sabbatical. And while I was on sabbatical at UC Davis, I was taking guitar lessons I can't remember the place in UC Davis now, but there was this guitarist and we were really experimenting with some, interesting guitar methods. But so I can attribute my time at UC Davis for launching my music career as it was. So about a year after I got back to the University of Washington, I started getting serious about music. We created a CD. Again, and if you want to go to the website, you can download it. We have some full videos of some of the songs, and some of them are just on MP3s. I should show you. I have, it's heavy metal. So I have my heavy metal guitars with, skulls and crossbones and all the cool stuff. So, to just give a little history, we kicked, by the time Metal Blade Records was interested in us, we kicked the singer out of the band and you'll understand why we kicked him out when you listen to the CD. But we did get a really good singer, but he was a real heavy metal guy, with drug problems and everything. And I had written 3 new songs. I said, look, we got to get this guy in the studio, send the demos to Metal Blade Records. We'll be millionaires and they'll all be over. But the guy had, he's missing rehearsals and stuff, but he had to go into rehab, and then we couldn't find another singer. And then I realized this is taking a lot of time, so I better go back and be a professor. But the students often ask me if you had been signed, would you what would you do? Would you be a professor or go into rock and roll? So it's obvious. I would be a rock star. Anybody can be a professor. But yeah, so that didn't work out. Although I should mention the album was released in 1994, and technically my band is eligible for the Rock and Roll Hall of Fame. So if you want to do a write-in vote, I think we sold like 2,000 CDs. So we're not quite up there with Jethro Tull and some of the other people that haven't been inducted yet. But there's like a 1 in a billion chance, right? Who's to say there's never a chance? But for rock and roll eligibility, you have to be 25 years out from your first CD. So
I think we felt lucky that you made the right choice for the transportation.
Yeah. But I think it's important to remember. And when you think about it, if I look back on my career, all of these sort of hobbies, you know, the motorcycle racing and the music, they all bring something back to what you actually do as a professor. And you can think about that as you're going through your career. You know, nothing is really a waste of time, because when you do something like, you know, there's a lot of, you know, things that I've done when I was racing motorcycles that gave me ideas to write papers, you know, that actually ended up, you know, some motorcycle safety papers that I've written and others. So, you know, nothing is really a waste of time. Even binging a Netflix series, you can probably get some ideas. And you know, it's been my experience is that the researchers that come up with really good ideas, usually it's other aspects of their life that motivate them to bring something from another aspect of life and bring it in, and something that, you know, people have never thought about viewing a problem that way before. So it's, you know, when somebody says, "Ah, you're watching too many Netflix series," it's like, no, you know, I'm gaining information that will help me, you know, propel my dissertation to new excellence or whatever.
Yeah, that's good to hear. And so if you this Netflix fans, don't feel guilty.
Now, on the other effect, if you're not actually processing data, it could be just a waste of time.
Right, it could be we've got a data garbage in, garbage out, or you have to use information intelligently. Yes. So Ray, I saw you raise your hand a few minutes ago. So Ray, you can ask your question.
Yeah, sure. Thank you, Fred. It was amazing. We have one more seminar this quarter, but I think your presentation would have been an excellent conclusion for this quarter. You mentioned, you talked about all this amazing information about models and also how to be a good academic person. But I was wondering if you can give us some advice on how to be a good modeler, given your background and your career, what it takes to be a fair and conscious modeler in transportation field.
Yeah, that's you know, that's a difficult. If I look over the many years, it's, you know, because when you collect data and when you develop models, you have inherent biases, and so I remember I had one student a few years back where she, you know, the statistical modelers was telling her that a variable she thought would be significant wasn't significant, but she insisted that it be in the model because I know it has to be significant. So what I think is important when you're developing statistical models or doing whatever is to let the data speak to you and then think about what it's saying. Because a lot, you know, when you go in to develop a model, you have an expectation of what's going to be an important explanatory variable. And invariably, when you start estimating the model, you find that what your expectations are not 100% correct, or your hypothesis or theory is not being supported. But there's often reasons for that that may not necessarily mean that your hypothesis or theory was incorrect, but they're different. The way the data become statistically significant, there could possibly be different explanations. And what I have noticed in recent years, probably since the early 2000s, when we start using the heterogeneity models with mixing distributions, is a lot of times the contradictory findings that we were coming up with using fixed parameters can now be explained because you have a distribution of parameters over the population. So I guess my recommendation for being a good modeler would be let the data talk to you and then think about what it's saying and then try to reconcile your theories and hypotheses before you started analyzing the data. Try to reconcile that with what the data is actually telling you. And a lot of times you're getting the contradictory, well, not a lot of times, but some of the times you get a contradictory result simply because of the estimation process. There's something you're not accounting for in the estimation process. So you may find a variable, it's statistically insignificant. But the reason why it's statistically insignificant is you may be modeling it as a fixed parameter when in fact it's significant, but it varies across the population. So if you use like a random parameters model, it is significant. But if you use a fixed parameters model, it's insignificant because you're not accounting for the distribution of effects across the population. So it's a constant balance between your hypothesis and theory and then what the data actually tells you. Now, sometimes they perfectly collide. You have an hypothesis, your data supports the hypothesis, and you're done. But almost always, when you start analyzing the data, but you have to be aware of the method that you're using, because the method that you're using constrains what the data can tell you. So it's a constant balance between those two, your hypothesis and what the data is telling you. But it's, every data set is different. And so, a lot of times, people say, well, which modeling approach is different? A lot of times it just depends on the variance in the data. Sometimes a mixed logit model would be better, and sometimes an ordered probability model would be better. You can't, it's often not a single method, completely dominates another.
Awesome, thank you.
Okay.
Any other questions from our student audience? You can raise your hand if you have.
And they can be questions on motorcycle racing and music too.
I can ask a question. Hi, Fred. Thank you very much for a very interesting talk. I think both your presentation was really good, and then after that, what you shared about your history, that was really interesting too. So we've actually been learning about predictive and inference models in our applied data analysis class, but I wasn't too sure about the heterogeneity models that you spoke of. Would you mind expanding a little bit on that?
So yeah, the heterogeneity models are models that use mixing distributions. So I'm not sure did you cover like the mixed logit models or random parameter models in your course? Maybe not. But these are these models. I guess the one paper that, and I don't have it up here. I wrote a paper in 2016 with Chandra Bhat. Did Chandra give a presentation?
Not yet.
Okay.
Well, in the future.
Yeah. But there's a 2016 paper that I wrote called Unobserved Heterogeneity in the Analysis of Highway Accident Data. So that paper would explain what these heterogeneity models are. But really what they are is they're random parameter models and latent class models. And what they try to do is they add a mixing distribution that allows the beta that you estimate to not be the same for everybody in the population. So for example, let's say I'm estimating let me give a good example. I'm estimating a model that predicts what type of car a person is going to buy. So let's go for a specific make and model of a car. So I know that rich people are going to be less sensitive to the price variable than poor people. So, I mean, one way that you do that with a fixed parameter models is you divide the price of the car divided by income. And then so that reduces the X for rich people and makes the X larger for poor people because they'll have a smaller income in the denominator. So what these mixing models do is say, okay, look, not everybody has the same beta for price. And I'm assuming that that beta is distributed over a population by some distribution, maybe a normal distribution or whatever. So when you use these heterogeneity models, they allow the individual parameters to be unique to each observation according to some distribution. So these heterogeneity models account for unobserved heterogeneity in the data. For some reason, rich people are going to be less sensitive to price, so they're going to have a lower beta, and poor people are going to be more sensitive to price, so they're going to have a higher beta. So these mixing distributions, and I guess these really started catching on in the safety and transportation fields, maybe in the early 2000s, when Dan McFadden and Kenneth Train, wrote some papers on the mixed logit. And Kenneth Train also has a book that's available online that looks at random parameter logit models. But these heterogeneity models, if you look at the chapters in my book, from chapter 16 on, they're all heterogeneity models. And it just allows you a lot more flexibility, because it allows you to look at betas instead of them being fixed across. Everybody gets the same beta. Potentially everybody could get a different beta. Or if you use a latent class or finite mixture model, groups of people have the same beta. So these models have become extremely popular in academic circles, not so much in economics, even though economists are the ones that first started developing this, because economists realize that these heterogeneity models don't completely resolve the issues of endogeneity and self-selectivity. In fact, they can confuse them, because you get these mixing distributions that capture some of it, but not all of it. So the economics field has sort of moved away from these and they're extremely complex and difficult, potentially difficult to estimate, although there are a lot of packages that will estimate, there's packages in R that estimate random parameter models. NLogit LimDep is a package that I use when I teach my classes using my book. So these heterogeneity models are just what I would classify as random parameter models, and latent class models are the two most popular heterogeneity models.
Thank you.
And I should mention, if you look at my journal, Analytic Methods and Accident Research, if you look at any paper in there, it has heterogeneity models, because if you don't use a heterogeneity model, I reject your paper. because you can show mathematically that the heterogeneity model fits better, almost always. Not always, but almost always. But yeah, so that, if you want to get caught up on that literature, that 2016 paper, Unobserved Heterogeneity in Highway Safety Data, is really good place to start, because it not only does the safety literature, but it talks about the evolution of heterogeneity models. And I think it's a Web of Science highly cited paper, so it should be easy to find.
Adia,
thanks, Michael. Fred, thank you so much for the presentation. Very interesting. Two questions. One related to your motorcycle racing world. Has that world and your modeling world collided to figure out better ways of how we do some of this? Just interested to know if there were any practical applications that came out of it. And a more academic question is, with increasing amount of technology-driven inputs into the vehicles now, are the current models good enough to be able to capture some of these kind of failures that lead to fatalities or crashes, as compared to modeling for human error that's been more prevalent so far?
Mm-hmm. So let me answer the first question. I think my motorcycle, there was my interest in motorcycling. One time I saw there was a Rider magazine, the motorcycle safety writer for Rider magazine did a survey. So I saw his survey because I was reading motorcycle magazines. This is like in the early 90s. I saw his survey and said, hey, I could do an analysis of this. And so we ended up writing a paper based on the data that I saw in this motorcycle publication. Now, unfortunately, he was killed in a motorcycle crash. I think in Texas, but he was very famous because he would teach motorcycling safety to like Mike Tyson and all sorts of celebrities, a very famous guy. But tragically, I mean, there are cases where, a deer comes out of nowhere and there's nothing you can do. So there's some risk involved. And I've also I've done a number of motorcycle safety, papers. Personally, I've experienced multiple crashes. One's been on the highway, and then the other 2 or 3 crashes have mostly been on racetracks. But fortunately, there's a saying when you race motorcycles, if you're not crashing, you're not going fast enough. So I was going fast enough a couple times. So I think at some level, those two, do collide. They have helped motivate. Now, your second question with regard to the technology, actually, if I did a paper in 2006 where we argued that safety features would actually be offset by more risky driving behavior. And actually, I think if you go to my website, I actually there's an interview I did for Good Morning America, like in 2006 or something, where our paper came out and we argued that there's offsetting behavior. That, in other words, you can think of it like this. I like to drive and I like to drive with a 1 in 10,000 chance of dying. So if you give me a safety feature like, anti-lock brakes or side impact airbags, whatever, that increases or decreases my chance of dying to 1 in 100,000, then I would just drive faster. So I don't take the benefit in that. There's still benefit to society because I'm driving faster, getting to my destination quicker. But I don't take it out as safety, and it ends up as being this offsetting behavior. So I think when we evaluate the effectiveness of vehicle attributes, we have to consider the potential offsetting behavior. Another interesting point, and this is something very important to consider, because this fits into what we were talking about with self-selectivity, when you look at a new safety feature and how effective it is, a lot of times when the National Highway Traffic Safety Administration does this, they look at people that are in crashes with side impact airbags, for example, and people in crashes without side impact airbags. And they say, well, side impact airbags are 80% effective in reducing fatality. But that's something you do not want to do, because that's something that's 100% wrong, because the people that buy cars with side impact airbags are probably the safest drivers, okay? And if you look at the estimated effectiveness of side impact airbags over time, I think their initial estimates were like 70%, then it became 50%, 40%, until you have the entire sample of the population, because the riskiest drivers are not going to have the side impact airbag cars for quite some time. It takes a while and so that self-selectivity that we were talking about affects results, because if you think of what NHTSA reports, they just look at the cars with side impact airbags, the cars without, but the drivers in those cars are much different. If you put the drivers in the cars with side impact airbags in the non-side impact airbag cars, they would probably have a higher, a lower probability of a crash, because the riskier drivers don't have the side impact cars. At some point, everybody will have them, and then you'll be able to assess the full effectiveness. But that's the same sort of self-selectivity identification problem they were talking about earlier with the causality. Now, what's also going to be interesting is when you're driving a car with advanced safety features, or anti-lock brakes that allow you to stop faster, or the Tesla that goes 0 to 60 in 1.1 seconds, accelerate quicker. Your behavior does not only affect your accident risk, everybody else around you starts adjusting to you. So that's, another paper that I wrote is this temporal instability of highway crash data. And the argument there is that technology is changing so quickly in the automotive industry that the betas that we estimate in 1 year are going to be different than in another year, because everything is changing. Everybody's behavior is adapting. And you're not only responding to the safety features in your car and the safety features that others have in cars around you, but then there's always social changes, right? Your cell phone distraction, everything is changing. And there have been a lot of papers that come out recently in my journal that show, statistical differences from year to year in the frequency of crashes and the severity of crashes. So this is what we call temporal instability that you can test for. And that's another big future direction, is we want to find out how people's betas change over time. And that's going to be something, the next generation of people, you and others, are going to have to deal with. You have this machine learning and stuff coming, but you have the great opportunities, you have the betas changing over time because of the new technologies, and you're going to have this era where you have the automated autonomous vehicles mixed with human vehicles. That's going to be fascinating. There's going to be like years of research on that. It's going to be great.
Thank you.
All right, I think I can open to the outside audience. I've noted there are a few questions in Q&A. So please ask your question as concise as you can, so we can go over all these questions if possible. So Linda, can you ask your question? Okay, so probably Linda is no longer with the, is probably sign up. And Sanho, are you still there? Well, I think they probably have already signed up, and so Fred, I have it's not really a question. It's a problem that we're actually encountering. It's Caltrans, they're interested in like hotspots, and also if they did something, whether it improved the safety or not, they want to evaluate project-based sort of safety impact. And the thing that for any particular location, these crashes are very small probability events, and oftentimes you don't have enough observations, and there are multiple factors contributing to the safety. So from your vantage point, like if you're going to evaluate before and after, what kind of method would be more suitable, like the heterogeneity or the traditional methods?
So yeah, this is a very good point, and it sort of gets back to what I was talking about with this temporal instability. Let me give you an example for if we look at crashes during the Great Recession. There's this general observation when the economic conditions of the country get bad, we end up with fewer crashes and fatalities per mile driven. So there's a fundamental, and then when the economy is good, you end up getting more vehicle crashes per mile driven. Now, there's a lot of theories and potential explanations for that about how people's risk perception evolved. There's neuroscience. A lot of my 2018 paper gets into a lot of details about this. Now, the problem is you have these sort of global trends that are based on economics, or over time, we know that there's a general downward trend in the number of fatalities per mile driven. So the problem when you do like before and after analysis is you have to see where you are in this economic trend. So for example, when we were in the Great Recession in the late 2000s, if you did a before and after analysis, almost anything you did was found to be very effective because the number of crashes per mile driven were naturally going down globally, okay, over time. So everything is effective. Now, I noticed that problem when we got to, when I got to the University of South Florida here. We started, they were doing, people in the Center for Urban Transportation Research here were doing studies where the economy was starting to pick up. So this is like 2016, 2017, and you're getting more, crashes per mile driven. So now you're doing these safety features, but you're finding almost every safety feature you use, if you do before and after analysis, it's gotten worse because globally, the risk of drivers is getting worse. So when you do before and after analysis, you have to take into account this sort of, this underlying temporal element that could sometimes give you contradictory findings. And a lot of traditional before and after analysis, like using empirical Bayes and stuff, runs into this temporal instability problem straight on. Now, I have not done a lot of hotspot, related, high accident location related research, but if I was giving a multi-million-dollar contract, and we can talk about that later, I think you could do a really interesting thing using heterogeneity models to account for those temporal effects. I'm currently doing a national cooperative highway research project that's looking at speed limits being raised in Kansas. And we developed this really interesting heterogeneity model that studies the effect of this. And we have a lot of temporal shifting going on. So it's not an easy problem because of these global trends. So, even if you knew that the betas were constant, that the overall crash rate per mile driven was the same, you would still potentially have a before and after problem. But when you have this global changing in the crash rates due to economic conditions or other factors, it becomes a more complicated problem. But it's not easy to solve, but it can be done with, I think, heterogeneity models would be the way to go. If you're talking about a specific project idea you have in mind, we can talk about it.
Yeah, it's a $150K project. So definitely, we a tenth of the budget that you mentioned.
Okay.
So we're looking at actually more, like if Caltrans have done something and what's the effectiveness on the safety improvement.
Yeah, it's still going to be sort of a difficult problem to address, but it's not impossible. And I think you can make you can definitely make some inferences. Perhaps we can talk at some point about that, and I can give you some.
I think we can talk offline and on that. I think we'll probably can schedule a Zoom meeting with you, with my students.
But that general phenomenon of fewer crashes per mile during recession, then it's not just the Great Recession. This goes back to recessions in like 1980, 1960. Anytime there's a recession, you get fewer crashes per mile driven. And again, if you look at my 2018 temporal instability paper, there's a lot of neuroscience reasons and stuff for that. But it makes the problem intellectually interesting, but empirically it makes it difficult.
Yeah, I was wondering, during the recession, a lot of, for example, construction work or delivery. So a lot of the people who probably drive fatigue and maybe there's a higher proportion of those. But when in a recession, you have a bigger reduction of those kind of travel. Well, that's just some. Yeah,
and that's one of the arguments is that the people driving. Now, this brings up a very interesting point, and I'm actually doing some work on this now. Is what happened during COVID? Because in this case, during COVID, the types of drivers that are on the road are a lot different during the COVID lockdowns, and so in this case, we have. And getting back to what I was talking about earlier, here you have the self-selectivity problem. Who's getting involved in crashes? So who's getting involved in crashes before COVID is going to be a lot different than who's getting involved in crashes during the COVID lockdowns, because the types of people that are going to be on the road are going to be a lot different, because the people that can work remotely are going to be working remotely. So this is, and we've collected data from Florida on this, but again, this is a research project that I have in the upcoming year, but it's really going to be, target that sort of self-selectivity issue, because the types of people being on the road are much different during the COVID lockdown. And it's sort of the idea that you're getting to, is that during a recession, you have different people using different proportions of the VMT, proportions of the mile travel. But during COVID is going to be a great example of that, because we're going to have like 3 or 4 months where the VMT being driven by certain people is going to be a lot different than it was pre-COVID.
Yeah, and this is a fascinating topic that we can go on and on, but our time 3 has passed, and so we'll stop here. And thank you, Fred, again for really exciting talk. And we'll stop here, and I wish everybody have a nice weekend.